Hello and welcome to Rice's Workbench, episode number 1. I recently wanted to play some old computer games on my Commodore 64, as every nerd would do. So I hooked it up, powered it on, and then it happened. I heard some sizzling noise, some crackling noise, and then the magic smoke escaped out of the primary power supply. Sadly, can't be that harsh after 30 years. So I thought, okay, let's fix it. I opened it up and then I saw this. The whole power supply is covered in some brown, probably cancer-causing epoxy and can't be fixed, sadly. So I thought, okay, let's rebuild it from the ground up. Same thing as the power supply of the floppy disk drive. I measured output. It has some high ripple on it, so probably the capacitors are dried up inside of it, and it's also covered in this brown epoxy, so it can't be fixed. Also, the capacitors in both of the units in the Commodore 64 and the floppy disk drive are also dried up. I measured it with an ESR meter, and they're all too high or have lost its capacitance, so they also need to be replaced. And I thought, well, why not make a video about it if those 2 viewers who actually watch this video have the same problem. So let's go to the bench and I show you what I've designed, and you can build it as well. So let's go. Okay, these are the 2 power supplies in question. That one over here is from the Commodore 64. I don't know if you can read it. That one requires 5 volt DC 1.7 amp. And that's the problem, 9 volt AC 1 amp. The 5 volt DC wouldn't that big of a problem, but the 9 volt AC is pretty much impossible to get a ready-made power supply nowadays with 9 volt AC. So we were pretty much stuck with building our own, or as some people on the internet would have done, using 2 power supplies, one for DC and one for AC, and wire it up through one power. Pretty much using 2 power supplies and wire it to one plug, which I don't like to do. It looks a bit messy. And there is one big problem with the old Commodore 64, so in general with old hardware like these, which don't like switch mode power supplies, which I'll explain shortly. And that's the other power supply we would try to replace. That one is a bit more straightforward. It requires 5 volt DC, 1 amp, and 12 volt DC half an amp, which could be, maybe you could buy a ready-made one, but if I need to design a new power supply for the Commodore 64 already, I could just design another one for the floppy disk drive. And as we see on the schematics afterwards, we can use the same design for both of the power supplies. We just have to replace the components on the PCB for each one, which pretty convenient. And that's the design I came up with. Same as the old power supplies. It's a linear transformer. I thought about it using direct switch mode from AC to DC, but there's a problem with the old designs like the Commodore 64. Usually in new pieces of electronics, it's not a big deal using a switch mode power supply direct from AC to DC. But on the Commodore 64 there's a big problem. That is, the connectors at the back side are simply accessible. It's like the expansion slots. You can touch them. And the problem with switch mode power supplies is there is some teeny tiny bit stray capacitance between the primary and secondary. And then what can happen is, because we have a high switching frequency, that the capacitance always can be discharged into the Commodore 64 expansion slots if you touch it. And that the voltage is about, well, what is it, 80 or 90 volts. And a small shock with a few picofarad capacitors, 80, 90 volts, could theoretically damage this Commodore 64. So I chose, well, pretty much stick in an old-fashioned linear transformer. Should be right. Can't go anything wrong with that. And of course we need a linear transformer for the 9 volt AC. I saw a few guys designing switch mode 1 and using the DC power supply and a full bridge to generate a square impulses for the 9-volt AC, which I don't like to do. Just stick to an old-fashioned linear power supply. Okay, first over here we come in with a 230 volts AC, go through a fuse to protect everything, a small filter capacitance over here, not really necessary, just put in for good measure, same as the voltage band regulator, voltage band resistor over here, just to protect the primary side against gross overvoltages from the grid. And then over here, that's our secondary side. As said, we can use the same power supply either for the Commodore 64 and the floppy disk drive. I will explain shortly how this works. First, we have up here, that's our 5-volt output. That's the same on both power supplies, because both power supplies need 5-volt DC. The output of the transformer over here goes first in the fuse to protect it. Again, voltage band resistor to protect the output against gross overvoltages. Then we go into a bridge rectifier, and then over here we have our primary filter capacitance with 3.3 microfarad to filter the AC the AC waveform and give us nice smooth DC, and this also forms our intermediate circuit. And over here we have a switch mode regulator, which is just an off-the-shelf made brick from Traco Power. Didn't want to design my own, just sticking a ready-made one. Should be right. What Traco recommends is this filter network over here. That's just 2 capacitors and a filter inductor, just to filter out the reflected ripple current. Also, I breadboarded the circuit already, and there was pretty much high ripple on that one, or ripple current on this capacitor, so I decided just to put it in for good measure. So that just stick to the recommended circuit, nothing can go wrong. That over here is a trim pot. That's to trim the output voltage just to exactly the value we want. In that case would be around 5 or 5.1 volt. And over here we have our protection Zener with 6.2 volt, which protects the output against also gross overvoltages. Not anything special. Maybe you could design a crowbar circuit here, but didn't want to go there. And over here we have a last filter capacitor or storage capacitor, which just buffers a little bit, little energy buffer for the output. Nothing special. And that over here is just a mirror image of the upper one. In this case, that would be the 12-volt output rail for the floppy disk drive. Just the same as the upper one, just with a different regulator on here. In the case of the Commodore 64 power supply, which would require 9-volt AC, there's just a different transformer in there with the same footprint, just a different type. That's the same. And over everything on here to the right side, we simply omit all the components here on the right side. Everything is simply bridged. So we can pretty much use the same PCB layout for both of the power supplies. We simply have to replace the components with different values or simply omit them. This over here would be the PCB layout. Pretty much the same thing as you saw on the schematics. That's our input, fuse, capacitor, voltage band resistor, and this is a primary side of a transformer. Theoretically, we could use the same circuit on 115 volts. You simply have to rewire the primary coils of the transformer. In our case, we use it for 230 volts AC, so both of the primary coils are in series, otherwise you have to put them in parallel. And here we got our 2 output sections, pretty much a mirror image of each other, mostly. One output over here first goes into the fuse, bridge rectifier, primary 3.3 millifarad filter capacitor, and then we got here our little filter for the switch mode power brick, and that's our switch mode power brick, trim pot, output filter, capacitor, and protection Zener, and output connector. Same thing up here. For the floppy disk drive, both of these will be populated. For the Commodore 64, one side would require 9-volt AC. And it's pretty much simple and straightforward. I just put in some dashed lines where I will put in a wire link just to bridge all the components to get the 9-volt AC from the transformer to the connector down there. So we would simply bridge all the components which aren't necessary and simply omit the components. And in this way we can use the same PCB for both of the power supplies, one for the Commodore 64 and for the floppy disk drive. Simply configure it differently and it will work. And through the magic of television, or in this case YouTube, we already have our PCB made. It's actually made by Worth Electronics, or Wirth Electronics, depending if you speak German or English. And over here we have our case for the power supply, which is a standard case from Bobla. Nothing special. That will be our strain relief for the connectors, one input and output. And the PCB itself, really nicely made from Wirth Electronics. Absolutely, the whole alignment is perfect. The silk screen, very nice. One of the nicer ones I ever got. And yeah, shouldn't be that much big of a problem. That one fits in like so. Well, that's at least the plan. Let's see if it works. Okay, and I would say let's go to soldering. Heat up the soldering iron and solder it together. And now this is the nearly finished power supply. I already populated all the fuses. And that over here. The only thing I left off is a protection zener. It might kick in too early, so I left it off so we can still adjust output voltage without shorting it out. And yeah, I like it. Especially the rack capacitors, they look awesome. They come from Worth Electronic. Nice. Now comes the fun part, powering it on. I'm ready. Okay, and this is our test setup. We've got the mains coming in over here from an isolation transformer. We measure voltage and current at the input. Here we have got our power supply under test. Here we have a DC load and 2 multimeters which measures voltage and current for the plus 5 volt DC. And over here we will measure the 9 volt AC. Here we've got the 9 volt electronic load for the 9 volt AC and 2 multimeters which will measure voltage and current. Now up here we've got an oscilloscope which will measure the intermediate voltage from the DC link capacitor, which stores the rectified AC voltage. We'll measure the output of the 5 volt regulator, and we will measure the DC wave the AC waveform from the 9 volt output. Now let's plug it in. Will the magic smoke escape? Ooh. Nothing's burning yet. Looks good. Yes. No flames, no fire. That's boring. First, let's test the 5 volt DC rail. We already got 5.1 volts, which is pretty good without even trimming. So let's set a constant current of 0.01, 10 milliamps. Let's see what happens. We've got 10 milliamps and still 5 volts. Awesome. Let's crank it up. 200 milliamps. Still good. One amp. Still hanging in there. Let's see, can we do 1.7? 1.7 amps, like the original, if not even better. Nothing's getting hot. Awesome, the voltage dropped just a teeny tiny bit, nothing to worry. Oh. Looks great. Now let's take a look at the oscilloscope. The yellow waveform is the DC link capacitor, which rectifies the AC mains, and the green one is the output voltage of the switch mode regulator. As you can see, we still have about 10 volts RMS in our capacitor stored, which is more than enough. And output voltage, this is channel 2, the green one, is exactly 5 volts. Awesome. Now for the 9 volt supply. Unloaded we've got 10.5 volts, which is pretty normal. And now let's switch on the load. Still works. Let's slowly wind the wick up. 40 milliamps. That one should deliver 1 amp. Let's see if we get there. It's a bit touchy, that's why I go slow. Half an amp, 600 milliamps, 700, 800, 900, and 1 amp. Awesome! Bit high on the voltage side, but still acceptable. Now to the oscilloscope. Let's see if we can get a shot at this. This is now with all the loads switched on. We've got our AC waveform, which looks a bit weird, but I think that's more to the load than to the transformer or our power supply. We've got a diesel link capacitor, which is nice and bumpy, and we got still our regulator 5 volts, which is exactly 5 volts. Awesome! It works perfectly. We're now measuring the ripple of the output. As you can see, the yellow waveform is still our intermediate circuit DC bus. That's the rectified AC. There we got 1.7 volts peak to peak, and so half a volt RMS. And the output of a regulator, which is awesome, 3 volt RMS and 120 volts peak to peak. Very nice regulator, I have to say. Absolutely no problem whatsoever. We're still on a full load with 1.7 amps. Looks nice. Okay, now let's do an overshoot test. I currently have unplugged it, and I will now plug it in and we will capture the power on cycle. Let's see what happens. Nice. No overshoot. Direct straight to it. Okay, yeah, bit of bounce there. There we can see rise of the intermediate voltage. There we can see the regulator ramp up. Very nice, that's a very nice regulator. This is without load. Now, of course, we will try it with the load. Let's see what happens. Plug it. Let's reset. Switch the load on. It's still set to 1.7 amps. Let's see what happens. Still exactly the same, a bit of whatever that is, but still very nice. 1% overshoot, literally nothing. Awesome, that regulator is very nice. There we can see the intermediate voltage wiggling its way up there. Well, what can I say? Very nice regulator. Perfect. And this is our power consumption of the unit during full load. That would be 24 watts at 230 volts and 119 milliamps. Very nice. Now let's switch it off. Well, let's switch the loads off. That will be the power consumption in standby. Oh, pretty good. Only 1.2 watts. That with a linear transformer. Awesome. Now this is our insulation transformer, and we will measuring the input current waveform to our power supply, which again, there's some weirdness over there. I think that's still the electronic load. Oops. Should go in the right direction. Damn touchscreens. Otherwise, very nice. Let's see the table. Same thing as the multimeter, and we've got a lambda of 0.923. Awesome. And that's measured under full load. Okay, let's take a look at the thermals of the power supply. We'll use a thermal camera. Let's take a look at the... What shall we look at? That's a DC to DC regulator. Oh, what have we got there? 40 to 50 degrees Celsius. Not hot at all. Awesome. Everything else is about 30 degrees. The only thing that gets hot is the bridge rectifier in the middle here, which is about 17 something degrees. And I left it on for about, what is it, about an hour at full load, which it will never be. But that's acceptable. The transformer, still 30 degrees. Nothing to write home about. Awesome. I think that's pretty okay. And the second power supply performs just as good as the first one. Yeah, just switch off, bastard. Awesome. Now for the final test, we will measure if we wired up the connectors correctly. So we'll plug it in. In this case, this is our 1541 power supply. Okay, we should have 5 volts between pin 1 and 2. That would be those two. 1 is plus, 2 is ground. See? Yep. That's correct. Awesome. And we should have 12 volts between 4 and 2. See? Yep, that's correct. Awesome. That was the floppy disk drive power supply. And now for the power supply of the Commodore 64. Okay. That one should be 5 volts DC between 5 and 2. 5 and 2. Where the hell are you? 5 and 2. Yep. Perfect. 5 volts. And we should get our 9 volt AC between 6 and 7. Should be those two up there. Perfect. Everything's in order. Let's try it on. Well, try it on. Try it out. And now for the big moment, we will power them on. Well, be afraid. Be very afraid. Here in the back we have got the power supplies, a floppy, got a Commodore 64, and here we got a screen. I hooked everything up and, well, let's switch them on. That's the power feed for the power supplies. Nothing's burning yet. Let's see if the floppy still works. Yes! Still works! No smoke, no flames. Yes! And now for the big test, the Commodore 64. Let's see if it catches fire. Yes! Still works after 30 years. Awesome! Hell yeah, syntax error, how I missed you. Anyway. Anyway, We managed to rebuild the new power supplies, and what's next? Next we will refurbish those two units, which means we clean them out and replace all the capacitors. Take a look at those PCBs if there is any oxidization inside. And yeah, I hope you liked my first episode, and if you want, join me in the next one. See ya!